Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to this lecture. In the previous two lectures, we studied frequency domain representation of continuous periodic and aperiodic signals. In this lecture, we are going to talk about frequency domain representation of discrete periodic signals. So, the topic today is frequency domain representation of discrete periodic signals. So, a brief outline of the lecture is as follows. First, we will define what are discrete time signals, then we will see that what is digital signal processing or discrete time signal processing. Then we will look at what is discretization and what is the process of measurement and discretization. Then we will look at frequency domain representation of discrete periodic signals, which basically will lead to the idea of discrete Fourier series. Then we will look at the periodicity property of discrete Fourier series, and we will also look at the relationship among the Fourier coefficients of a discrete Fourier series. Then we will look at what is inverse discrete Fourier series, and at the end we will take an example to understand what is discrete Fourier series. So, let us first of all look at what are discrete time signals. So, a discrete time signal is a signal in which the independent variable is time, and the signal is defined at discrete values of time. Okay. So, discrete time signal is a signal where the independent variable is time and the signal is defined at discrete values of time. So, in this signal the amplitude of the signal is continuous, right. The amplitude of the signal is continuous. It can take any value, right. But if the amplitude is also quantized, okay, and discretized and converted to a binary representation, then such a discrete signal then becomes a digital signal. Okay. So, then it becomes a digital signal. So, in a digital signal we have the amplitude is also discretized. And represented in binary form. Okay. So, now let us see what is DSP. What is discrete time signal processing. It is also sometimes referred as digital signal processing. So, in discrete time signal processing, basically the analog signal is discretized and then the discrete version of the analog signal is processed. So, here the analog signal which basically is another name for continuous signal. Okay, is discretized, okay, and the discrete signal is processed. Okay. So, henceforth now we will refer discrete time signal just as discrete signal, right. So, there is another processing technique called analog signal processing. So, in analog signal processing, basically the analog signal is processed using analog circuits and hardware, right, and therefore the range of functions or the processing signal processing tasks that can be implemented are limited. So, in analog signal processing, analog signal is processed using analog circuits and hardware. So, because analog circuits and hardware is used to process the signal, the range of functions, mathematical functions through which the signal can be processed, they are limited. In DSP, which is digital signal processing or discrete time signal processing, microprocessors are used, right, which basically are based on digital circuits. So, these processors have high speed and are programmable. Therefore, a very wide range of signal processing tasks can be implemented using digital signal processing, and that is why most of the modern signal analyzers, they are based on DSP technology, right. Therefore, most modern signal processors are based on DSP technology. So, how discretization is done? So, in DSP, how discretization is done? So, in a DSP processor, the discretization is done using the process of what is called as periodic sampling, right. So, periodic sampling is done, right, which basically involves recording the signal at after every time interval delta t, right. This involves recording the signal after interval delta t, okay. So, elapse of every interval delta t, the signal is recorded, and therefore, delta t basically therefore depends on what is the sampling frequency of the signal. Okay. So, sampling frequency often represented by f subscript s is nothing but 1 upon delta t, okay, that is simply 1 upon delta t. So, this sampling frequency of the processor decides that what is this sampling interval delta t. So, therefore, if a continuous signal x of t, when it is discretized using frequency fs, right, then it is going to lead to discrete samples of the signal, and let us say if the samples are recorded over a length of time capital T, and if there are n samples, then over that period, then we will have the discrete signal that can be represented as n x n delta t is equal to x naught delta t, then we have x 1 delta t, then we have x 2 delta t, going up to x n minus 1 delta t, right. So, in this way this vector there are n samples, the vector has this recorded signal has n samples. So, therefore, this is nothing but the discrete signal, and for simplicity we can drop delta t and simply represent the discrete signal as x n, which consists of the samples x 1, x naught, x 1, x 2 going up to x n minus 1. So, this is nothing but the discrete signal. Now, what is the process of measurement and discretization? Let us look at some of the broad steps which are involved in the process of measurement and discretization. So, process of measurement and discretization. So, we can represent it through this simple block diagram. First we have the transducer like this, then we have signal conditioner, then we have analog to digital converter, so this is nothing but A to D converter, and the function of the A to D converter can be represented by two processes, and for the purpose of explanation I am representing it as two processes in sequence. So, the first process is process of discretization, and the next process is the process of digitization. So, therefore, we have first of all the signal which is analog signal x of t, which is sensed by the transducer, right, and then it is conditioned by the signal conditioner, and that generates a proportionate say voltage signal, right. So, that is typically the most of the so that is typically the situation most of the times, that a transducer and signal conditioner together converts a signal like say displacement signal or excitation signal into a proportionate voltage signal. So, therefore, this x of t is an analog signal. Then it converts it to a analog voltage signal. Now, A to D converter basically performs the discretization of this signal, right, and that depends on what is the sampling frequency. So, at a certain sampling frequency, this discretization process in the A to D converter would convert this analog voltage signal, right. It will record this analog voltage signal at discrete instance of time, okay, and the output of this discretization process will be a discrete signal Vk, right. So, it is a sequence, Vk is the discrete signal, discrete voltage signal, and then the process of digitization will basically quantize the amplitudes of the this discrete samples of the signal, right, and convert them into binary form, and at the end of this we will have a digital signal, okay, VDK. So, this is discrete signal Vk, and then we have a digital signal. So, these are the basically broad steps through which the signal undergoes, right, in the process of measurement and discretization. And since we would know the sensitivity of the transducer and signal conditioner together, right, then it will be possible for us to retrieve back the signal in the units of analog signal x of t, right. So, if I want to know what is the signal, say the discrete signal in the units of signal x of t, then I can obtain that as using the sensitivity, right. I can divide Vk by the sensitivity of the transducer, right, sensitivity expressed in terms of the voltage per unit unit of signal x. So, in this way I can find out the discrete signal xk. So, in this way we have now understood that what is discrete signal and how it is recorded, and now we are going to see how this signal is analyzed to obtain the frequency domain representation of this signal. So, frequency domain representation of discrete periodic signal. So, here now we are assuming that the signal we have recorded, that is say x of n, the discrete signal, right, it is a periodic discrete signal, it is a periodic signal. So, this is discrete signal x of n, and let us say it is a periodic signal. So, now to obtain the frequency domain representation of this, we basically start from the frequency domain representation of a continuous signal, of a periodic continuous signal. Now, since x of n is periodic, it has a period, right. So, it means it repeats after a certain number of samples. So, let us say n is the period of the signal, correct. Let us represent the continuous signal first, say this is x of t, and let us say that this is a simple signal, sine signal like this, right. And when it is discretized, we will have x of n like this, and let us suppose that the signal is like this, okay. So, let us say this is the signal. So, we have this is say the sample 0, then 1, 2, and then this goes up to n minus 1, right. So, and this step, the interval between time interval between every two consecutive samples is basically delta t, right, and then the sample the time period of the signal is t, correct. So, and here we see that t is basically equal to n into delta t. So, here therefore, n is the period of the signal in terms of the number of samples, and t is the capital T is the time period of the signal. And here we are saying that xn is periodic. So, therefore, now we start from the frequency domain representation of a continuous periodic signal. So, for a continuous periodic signal, we already know from the Fourier analysis that the kth frequency component right, we can write as Ck is equal to 1 by t integration of integration over 0 to t, that is one time period, and then x of t e to the power minus I k omega naught t dt. So, this is the expression we got in the in one of the previous lectures earlier, where we considered the frequency domain representation of a continuous periodic signal, right, and then we develop the complex form of the Fourier series expansion. Okay. So, this is nothing but this is from the complex form of the Fourier series expansion. And now what we are going to do, because the signal in the present case is discrete, now we are going to incorporate modifications in various variables, right, in this expression to account for the discrete nature of the signal. Okay. So, now what are those modifications? So, what we see is that the time t, okay, it is no longer continuous, but it is discrete. So, we can write t, the time instant of any particular sample of the signal, as n times delta t, right. So, if I substitute n is equal to 0, I get the time instant of the first sample, then if I substitute n is equal to 1, I get the time instant of the second sample, and if I substitute small n is equal to capital N minus 1, I get the time instant of the last sample, that is the nth sample. Then we also have the fundamental frequency omega naught. We know that this is equal to 2 pi upon the time period t, and in our case this would be t is nothing but n times delta t. T, already we have written the expression t, capital T, the time period, is nothing but equal to number of samples n multiplied by the time resolution or time gap delta t. The other thing is that the dt, it is an infinite simul time length, right. So, in the present case, this infinite simul time length this would become a finite time step delta t, right. So, this basically should be then replaced by delta t, right. And then because we have finite number of discrete number of samples, the signal is no longer continuous. So, we can't integrate the signal treating it as a continuous signal. So, the sign of integration has to be replaced by sign of summation, because the samples are discrete, they are finite in number, and we can carry out a finite summation. Therefore, integration 0 to capital T has to be replaced by summation, right, over the number of samples, and those samples would be varying from n is equal to 0 to n minus 1, right. And let us also represent the coefficient Ck by a new symbol, let us say capital X k. So, since small x we are using it to represent a discrete signal, right, in the time domain, we are using the capital X to represent the frequency domain representation of the signal, that is the signal in the frequency domain. So, now if we incorporate these modifications in this expression, then let us go to next page, and now we can write down, let us write down the expression for Ck again. So, we have 1 upon t integration from 0 to capital T, we have x of t into e to the power minus I k omega naught t into dt, right. Now, Ck we represented by x of k, right, and capital T is nothing but n into delta t, then integration is replaced by summation over the samples from 0 to n minus 1. X of t would no longer be a continuous signal, but it is a discrete signal. So, we will represent it by x of n, right, into e to the power minus I k omega naught is nothing but 2 pi upon time period t, and time period t was nothing but n into delta t, right, and small t is the discrete time instant, and that is nothing but small n into delta t, right, and dt is nothing but the finite time step delta t. So, we see from here that this delta t cancels out, and then we are left with 1 by n is equal to 0 to n minus 1 x of n e to the power minus I k 2 pi by n into n, because this delta t also cancels out from here, right, and then this is nothing but x of k. So, this is the expression we are now getting for x of k. Okay. And here k basically are the k is the index of the frequency component, right, and k can vary from minus infinity to plus infinity, all those components. So, I can have minus 2, then minus 1, then 0, then 1, then 2, and like this it will go up to infinity. Therefore, using this expression I can find the value of xk for k varying from minus infinity to plus infinity. So, xk essentially represents the frequency domain representation of the discrete signal x of n, right. Therefore, xk represents a frequency domain representation of discrete signal x of n, right, and this is called discrete Fourier series. Okay. So, this is referred as discrete Fourier series, right, and here the amplitudes xk, they are basically complex. The amplitude xk is complex, that is, it has magnitude and phase. Okay. Let us look at a very important property of this discrete Fourier series, which we are going to abbreviate as DFS, right. There is a very important property of DFS, right, and that property is that the discrete Fourier series is periodic. Let us try to look at that, why discrete Fourier series is periodic. So, we are going to now look at and study the periodicity of DFS, the discrete Fourier series. Let us look at rth and r plus nth frequency components. So, we got the expression for xk. So, if we substitute k is equal to r, we can find xr and we can write that as 1 by n summation from n is equal to 0 to n minus 1, right, and then x of n into e to the power minus I. So, now in place of k we have to write r. So, r into 2 pi by capital N into small n, right. So, this is the expression, and similarly for x r plus n we can write down 1 by n is equal to 0 to n minus 1 x n e to the power minus I r plus n 2 pi by n into n, right, and this I can write as 1 upon n is equal to 0 to n minus 1, right, into x n e to the power minus I r 2 pi by n into small n into, right, minus e to the power minus I n 2 pi by n into small n, right, and therefore, this quantity is, if you look at this quantity, and this quantity is nothing but e to the power minus I 2 pi n, right, and this is always equal to 1 because n is integer. Since n is integer, e to the power minus I 2 pi n is always 1, and therefore, this expression the coefficient x r plus n becomes n equal to 0 to n minus 1 x n e to the power minus I r 2 pi upon capital N into small n. this is x r plus n. So, what is the conclusion? We see that x r plus n in fact has turned out to be same as x r. This is nothing but equal to x r. So, x r plus n is actually equal to x r, right. So, this shows that, and this is true for any r, because we have not taken any specific r here, r is general. Therefore, we see that the frequency components whose indices are separated by capital N, they are identical, right, their amplitude is identical. So, if I take, let us say k from, if I look at the first n components, okay, then they are k is equal to 0, then 1, then 2 up to n minus 1. So, what are these? These are the first n components, okay. And then if I take further, right, if I go further, say n, then n plus 1 going up to say to n minus 1. So, these are next n components, right, and in this way I can go further, right. Because of the result we got previously, that is x r plus n is equal to x r. So, all these next n components, they will be identical to the first n components. So, these next n components, they are going to be same as first n components we got. So, from here we see that the discrete Fourier series is periodic, it is periodic, okay. And what is the periodicity of the discrete Fourier series? If you look at the frequency components you are getting, right. So, if I look at k is equal to 0, 1, 2 up to n minus 1, then what are the corresponding frequency components? The frequency components are 2 pi upon n delta t, okay, into 0, that is the frequency of the first component. Then I have 1 into 2 pi upon n delta t, that is the frequency of the next frequency component, and this would go up to n minus 1 into 2 pi upon n delta t, that is the frequency of the last frequency component, and the next frequency component would be n into 2 pi n delta t, correct. And therefore, the periodicity in the frequency domain right would be simply n into 2 pi upon n delta t, which basically means that 2 pi into the sampling frequency, which is nothing but the sampling frequency in radians per second. So, it means after a frequency range which is whose higher frequency is omega s, after that the frequency spectrum would repeat, the discrete Fourier series would repeat. Therefore, we see that discrete Fourier series DFS has n distinct frequency components, okay. And therefore, these n distinct components, they are basically, they form the frequency domain representation of the discrete periodic signal, right. And these components form the frequency domain representation of the discrete periodic signal. And then the k we can also take from, say I can take from minus n by 2, then minus n by 2 plus 1 going up to 0, then 1, then 2 going up to n by 2 minus 1. So, I can take this indices k from minus n by 2 to n by 2 minus 1, okay. This also can be taken. So, but then you can see these are also again n components, these are also essentially a total n components. Now, this n components, they also have certain dependency, okay, in terms of the their magnitude and phase, right, they are related to each other. So, let us look at that. Relationship among Fourier coefficients of DFS. Let us look at these relationships, right. First relationship we got was that x n plus k is equal to xk, right. So, the component k and n plus k they have same amplitude. Now, if I take k as minus k, then I can write this relationship simply as x n minus k is equal to x minus k, right. And from the discrete Fourier series expression, we can easily see that x minus k is essentially complex conjugate of the xk, correct. So, x minus k is complex conjugate of xk, and therefore, if I combine these two equations, then we can simply say that x n minus k is equal to x k complex conjugate, right. So, this is another relationship we get, okay. And what is meaning of this? This basically shows that the magnitude of x n minus k is same as magnitude of xk, right, and the phase of x n minus k is equal to minus of phase of xk, right. Now, what is the consequence of this property? That the magnitude spectrum of DFS is symmetric, and the consequence of this is that the phase spectrum is asymmetric. So, to get insight into the nature of the magnitude and phase spectrum, let us take a small example. Let us say that the discrete signal has 4 samples, right, and now if we find the DFS, then we will have 4 distinct frequency components that we will get, and those frequency components would be frequency components in DFS. What would they be? X naught, then we will have x1, then x2 and x3. These are the components we will have, right, k varying from this is, if I write k here, so k is equal to 0, k is equal to 1, k is equal to 2 and k is equal to 3, right. So, those are the components we will have. Now, let us look at the nature of these components, right. So, if you look at say x naught, so if we have the relationship that x minus k is equal to x k star. X minus k and x is basically complex conjugate of x k, right. So, if I take k is equal to 0, then what do I get? We get x 0 is equal to x star 0. So, x naught is nothing but complex conjugate of itself. So, that can happen only when x naught is real, it cannot be complex. So, x naught is real, that is the conclusion. Let us now look at the relationship x, we had n minus k, right, is equal to x star k. This also relationship we just got previously, right. So, if we take now k is equal to 1 here, so what we see? We see that 4 minus 1 is equal to x star 1, which means that x3 is equal to x star 1. So, this shows that the third frequency component, it is complex conjugate of the first frequency component, right. So, let us see for k is equal to 2, we know that x n minus k is equal to x star k, right. So, if I take k is equal to 2 and n is equal to 4, then this is x2 is equal to x2 star. So, this again shows that the x2 is basically real, right. Let us also look at this relationship x n minus k is equal to x k star when k is equal to 0. Then what do we get? We get x4, because n is 4, is equal to x star 0, and because x0 is real, so we can simply write this as x0. So, x4 is equal to x0. So, therefore, what we see, if we look at now the components x0, x1, x2, x3, so these are the n distinct components we have, and the next component in the next part of the period would be x4, right. So, what we see now, if you use the results we got, then this is nothing but x0, then x1, and then we have x2, and then x3 is nothing but the complex conjugate. Now, x3 is nothing but complex conjugate of x1, right. So, I can replace x3 by x1 star, and x4 is nothing but x0. So, I get this, right. So, therefore, what we see from here, that the spectrum is symmetric. The magnitude, if you look at, now if I look at the magnitude, then that is nothing but x0, then x1 magnitude, then x2 magnitude, and this is nothing but magnitude of x1 itself, because the x1 and its complex conjugate will have the same magnitude, and then I have x0. And what we see? Now, we see that this is symmetric with respect to sample x2, right. So, that is what is basically the meaning of the statement we made previously, that the magnitude spectrum of DFS is symmetric. So, in this case we see that this is symmetric, and if you look at the phase, right, then you can see the phase is basically asymmetric. It is very clear from here that because x2 and x0 they are real, while x1 and x3 they are complex conjugate of each other, and therefore they have a phase which differs by 180 degree. So, it is asymmetric. Let us now look at the inverse discrete Fourier series. So, once we obtain the Fourier coefficients xk, then how can we construct or reconstruct or regenerate the discrete sequence or discrete time signal, right? That can be done using inverse Fourier series. To obtain an expression for inverse discrete Fourier series, we again will start from the corresponding expression based on the continuous time signal, and for the continuous time signal, x of t is equal to Ck e to the power I k omega naught t, right, with k varying from minus infinity to plus infinity. So, this is the complex form of Fourier series expansion, okay. And now here we are going to incorporate the modifications in various variables here, taking into account the discrete nature of the signal. And therefore, now x of t we can simply represent as now discrete signal, right, xn, and then we have the summation. So, the number of frequency components we have got, they are n distinct frequency components we have, and therefore, we will use only those n distinct frequency components to reconstruct the signal, and hence we are going to use the components from k is equal to 0 to n minus 1, right. And then in place of Ck we have xk representing the discrete Fourier series, and then we have I k. In place of omega naught we now have the frequency 2 pi upon n delta t, right, which is nothing but the time period t into, now t is no longer continuous. So, and it exists only at discrete values of time, and that is nothing but small n into delta t. So, this cancels out, and then we are left with x n is equal to k is equal to 0 to n minus 1 x k e to the power I k 2 pi by capital N into small n. So, this is nothing but the expression for inverse DFS. So, if xk is given, the discrete Fourier series is given, Fourier coefficients are given, then we can find out or reconstruct the time sequence xn, the discrete sequence xn. Let us now take an example to understand how the magnitude spectrum in DFS looks like. So, example, let us take a signal, say x of t is equal to 20 cos 2 pi 2t plus 14 cos 2 pi 60. So, let us say this describes the signal we are measuring, this equation describes the signal we are measuring, and we see that this consists of, there are two frequency components, the one frequency component exists at 2 hertz and its amplitude is 20, and another frequency component exists at 6 hertz, its amplitude is 14. Let us say that we use a sampling frequency of 20 hertz to sample the signal, right, and the signal is recorded over a duration of 1 second. Therefore, the number of samples would be basically equal to 20, okay, and the fundamental frequency of the signal is 2 pi by t, which is 2 pi radian per second, and in terms of hertz this would be simply omega naught upon 2 pi, that is 1 hertz. Okay. So, that is basically going to be the frequency resolution between two consecutive frequency components, the frequency gap between two consecutive frequency components. Now, what we do is that we compute DFS, and we know that the periodicity of DFS, that would be basically equal to 20 hertz, the periodicity, that is, which is basically equal to the sampling frequency Fs. Okay. And now we compute the frequency components in DFS, and we can now compute, if you take the indices from say minus n by 2 to 0, 1 going up to n by 2 minus 1, right, and since n is 20, we are going to compute it from minus 10, minus 9, 0, 1, 2 up to 9. So, the corresponding frequency components would be, the frequencies would be minus 10 hertz, right, minus 9 hertz going up to 9 hertz, like this. So, that is basically the one period of DFS. And then similarly we can then find out from say 10 hertz to 30 hertz will be the second period. So we can go from say then 10, 11 up to 29 hertz, that will be the second period of DFS, and so on. So that will be basically repeating. So if we show it on the graph of, so this is nothing but now the magnitude of DFS, and here we are showing the frequency in hertz. So the we are therefore going to have the spectrum from -10 to 9 hertz. So then in the next sample will be at 10 hertz. So now we are going to basically have the one component that would appear here would be at 2 hertz, okay, and similarly at -2 hertz like this, and the amplitude of this component would be 10, and similarly there will be another component at 6 hertz and at -6 hertz, and the amplitude of this component would be 7. And then what will happen if we compute from 10 to 29 hertz, then that would appear, that would be repetition of this spectrum from -10 to +10. So we will have from say, let us suppose this is, let me extend axis further like this, and now let me show this is now 30 hertz, right. So now we are going to have a component at here corresponding to 6 hertz. So this component of course is at repetition, right. So this will be at a higher frequency, and then we have spectrum like this. Similarly on this side also it will repeat, okay, like this. So therefore this is essentially the one period of the DFS, and this basically repeats. So in this way we come to the end of the lecture, and today we have discussed the frequency domain representation of discrete periodic signals. Thank you.